So a quick recap of what we started with 10.2 is just talking about correlation. Specifically, you need to be able to interpret R ranging between -1 and 1. Closer to 1 or -1 we call strong, so that's kind of this right here. And closer to 0, so kind of between -7 and +0.7, we call that relatively weak. We are going to be using, we're going to be using this to interpret graphs. We're looking for there to be no pattern. This one's pretty good. It's probably actually better than the last one, but the idea is we're looking for no pattern because this creates kind of a real curve kind of away from it. This is definitely bad. Pattern is bad. This kind of clumping and then an outlier, bad. We really don't want there to be outliers. Ultimately, we're going to be evaluating this by looking at R, looking at the picture, and then justifying that with the residual plot. They also talk about, this is once again, this is all review, so I'll kind of keep going past this. They then talk about running a hypothesis test. This is great. There's going to be a couple homework questions on this. We went through how to do this in the calculator. Once you put it in A and B, basically we go to right over here, A, B. All right, so to run the test, I'll just recap and just quick review. Statistics, it's a test, and it's linear regression t-test. X-list was in A, Y-list in B, and put the results over in at least C. And then we were running whether faux is equal to, or not equal to 0 is the alternative, basically proving if it's not equal to 0, we're proving that there is a linear correlation, there's some relationship. So like I said, we did this in class, but I wanted to make sure to review it. These are the results we got: test statistic, p-value, degrees of freedom. It also gave us the linear regression equation. That's going to be something we spend a little more time on, okay? But once again, this is not something I am really stressed about for the test. You can use it for the test, but you do not have to, because by the time we do this, you'll have already had the other three things. So you literally could just run the test, okay? All right, so I'm going to scoot this down. We ran the whole test. We talked about these are the three things I would focus on as far as checking linearity. And then we did the least squared regression line. Well, sort of. We gave you the formula. We discussed that the slope makes sense that it would be the standard deviation of y over the standard deviation of x, rise over run. And then we multiply it by r. That gives us the strength and the direction of the relationship. Okay. And then we plug in the means and we solve for a. That's the second thing we'll do. And then we get the equation. So what I did is I actually ran 2 var stats, but you don't need to stress about that. That's something we've done before. But these are the statistics from that list of data. From that, how would I come up with this equation? Well, 1, I would take SY, 5.25085, divided by SX, 621.969. Now, if there was a perfect linear relationship, this would be our slope. We would be done, right? We would be a perfect situation, but we need to factor in the R, so we multiply that times R, negative 0.9439. Okay, so 5.25085. Let's do this in the scratch pad here. 5.2085. Let me see. 25085. So I think I missed something there. 25085. And I have a lot of decimals on this just so we can have as little round off error as possible. Divided by 621,969. 621. So divided by 621,969. And then that will be times R, which was 0.9439, it looks like. Make sure 0.9439. 621.969. That should do it. So this gives us our slope, 0.00797. So our slope, or our B, is 0.00797. How do we get the y-intercept? Well, A is equal to y bar, which was 30.7143, minus B, that 0.00797, times x bar, which is 3009.29. So 30.7143 minus the slope, I'll just grab the answer so I have a little more decimals, times 3009.29. 3009.29. So our y-intercept looks like it is 6.7342. Sure, 6.7342. All right, so basically what we have now is we can write the equation from this. Our y hat, also known as the predicting line, is equal to the y-intercept, 6.7342. And I thought that slope was supposed to be negative. I must have missed the negative. Let me double check. Oh, I forgot the negative there. So, yeah, the slope was supposed to be negative. Sorry about the negative 0.0079. Make sure I get that here. So, minus 0.00797x. There will be a question like that on the test where I give you the table and you fill it in and you find that slope by hand. I do not want you to do that. I do not want you to do that on the homework, okay? What I want you to do on the homework is go, man, that's a lot of work. Menu, statistics, calculations, linear regression. This will give us linear regression. You can run the test and it will also give you linear regression, but this will do it. So the a plus bx, because we want the y-intercept first. Our x list was in A. Our y list is in B. Category, don't need to mess with any of that. Results, I need to put them in C. Our A is off. What did I do? Is our B? I think our B was dead on. So I might have messed up on one of the means. Let me double check. And if you see it already, you're probably screaming at your screen, which doesn't help me, but thanks. So 30 minus... Oh. Okay. It's 30 minus the slope. So some of you are like, yeah, I knew you made a mistake. So it's 30 minus the slope, and the slope was negative 0.7007. So it's 30 minus the slope, gives me a y-intercept of 54.6944. So be careful with that. So let's see if I can erase that. And we'll put 59.69. Sorry about that. So yeah, minus a negative makes that a big old plus, basically. And 54.69, see how that compares here, 54.69. We're looking good on that, 695. All right, so keep in mind, that's all you have to do to get this linear regression is go to Stat, Calc, linear regression, A plus BX. and it gives me the A, it gives me the B, it also gives me the R and the R squared. The R right there is that negative 0.9439, so those are all things that they're going to give us, okay? All right, it also gives us a table of residuals. We'll talk about those as we keep going. But what can we do with this line? Well, if it's a good linear model, and we already decided that it was, then I can basically, oops. If it's a good linear model, then I can basically use it to predict. And that's the last thing they're asking us to do, is they're saying at 3,000 pounds, if you have a 3,000 pound car, what would you predict the miles per gallon to be? Okay, well, that 3,000 pounds is an X. This line, Y hat, is a predicted Y value. I plug in that X, that 3,000 for the X, and I get out a Y, or a predicted Y. So literally it's just Y hat is equal to 59.695 minus 0.00797 times the X. And that will give us a predicted value. So back to my scratch pad, 54.695. That's using the one that's not rounded off, and then we had minus 0.00797 times the X, which is 3,000, and we have 30.785. That's our predicted Y hat was 30.785. So at 3,000 pounds, we predict a 30.785 miles per gallon. So when can we do this? When can we use it to predict? Well, if the linear regression is a good model. I encouraged you to look at three things. They're talking about a whole test here. I just say first, check the R. There's a strong R. That's a good argument for a good model. Is that everything? No. Second, we sketch a graph. Does that graph appear linear? If it's linear, then we keep going. Third, we check the residual plot. The residual plot is where I graph that against the residuals. I think I might still have that in my calculator. Let me see. There we go. And we added the residual plot. There should be no pattern in the residuals. So those are the three things that you can do. And if that makes it a good linear model, then we can use it to predict. Be careful. Avoid what's called extrapolation. Extrapolation is predicting outside a collected data. So, like, I'm not going to say, well, what would the miles per gallon be for a 50-pound car? Well, if I looked at my original data, we didn't have any cars that were 50 pounds. That's utterly ridiculous. You go, well, what would the miles per gallon be for a tank? That doesn't make any sense. This works for vehicles weighing between, it looks like about 2,000 to about the mid 3,000s. That's the data we collected. That's what we should predict between. Do not predict outside that data. That is called extrapolation. All right, so these last three questions, I'm going to go kind of deep into these, but I basically have have taken and already typed these numbers in, so if you need to pause it and type it in, do that. But we have mother's height, daughter's height. First things first, let's get the equation. So mother's height, daughter's height, typed in, hopefully correctly. How do I get the least squared regression line? I can run a test. I don't recommend it. I would just do calculations, linear regression, a plus bx. X list was in A. How about A bracket? Y list was in B bracket. Put the results in C. Here's our regression equation. 22.95, 0.63. I'm going to write that down. So 22.95 plus the B, which is 0.639 X. I would also take a second now and put R, because that's the first thing that's going to tell me, should I use this to predict? Well, we got 0.692. That's kind of right on the edge. It's outside of that threshold. So what we're going to do is say, well, let's look at the other things, but this right here isn't going to be super strong at predicting. Okay, so how do I check it? Well, we graph it. So this is actually, we'll say, really somewhat weak. It's really kind of on that edge. But 2, if I graph it, the X, make sure you've named these, was the mother's height. Sure I'm doing that right. Yeah. And the Y was the daughter's height. So we're using the mother's height to predict the daughter's height, DH. How does that look? Well, there's a nice kind of linear trend. You can actually add the line to this, analyze, regression, show that A plus BX. There's that equation. Nice little sketch there. So most of those points fall along there. We have one outlier. This one has a pretty extreme effect on the graph. So this would be the point that kind of reduced our R, but the rest of them are good. You might look at this and go, well, did I just type that number in wrong? Or maybe this is just somebody that's just different. So 63, 58.6, 63, 58.6. So there's our culprit right there, kind of the one that's way off that would have a high residual. Okay? All right, so we would sketch this. Dot, dot, dot. Way down there. Then 1, 2, 3, 4. And then we have the line kind of going through there. It's a sketch. But this actually appears relatively linear. So this checks out. Third, what I would do is I would say, okay, well then let's just at least see what the residual looks like. To get the residual, we add that menu, analyze, residuals, number 2, show that residual plot. Sketch it. Dot, dot, dot. And way below. And close, close above. And there and right above it. So most of these are falling pretty close. There's no pattern. So this would be a pretty good linear model. I would use this to predict. Definitely would be somewhat weak, so it wouldn't be a very strong prediction, but we could use this. So this checks out as a linear model. Okay. Notice that point that was way off here is way off there, you can actually tap it and see that number that's way off here. There is its residual. It's off by 4.62 negative. The ones that are above, I can trace over them and it'll tell me their residuals. We'll be dealing with that kind of at the end. Okay, so the question is then to say, well, predict the daughter's height given the mother's height is 66. That 66 is a mother's height. That is an x. And they want us to predict. We will use a prediction line. Y hat is equal to A 22.95 plus 0.639 times that x. So 22.95 plus, what was the slope? 0.639 times the height of 66 inches. So with a mother's height of 66, we predict the daughter will be 65.124 inches. That is a predicted Y. Rinse and redo. Another classic application is temperature and number of times a cricket chirps. So listed below are the number of chirps in a minute and the corresponding temperatures. Is there a linear correlation? Well, first, let's get the equation, look at R. Like I said, I've already typed these in, so if you need to pause this and type them in, you can. But we're looking at chirps. And we're looking at temp. Oops, come on now. There we go. All right, so get those typed in. How do I get the linear regression equation? Menu, statistics, calculations. There it is, linear regression. We're going to use A plus BX. Okay, this is going to be a pain for me. Let's try hitting enter. I hope yours is working better than mine. Let's see. How about number 4? There we go. Our X list is in A. Our Y list is in B. Just make sure the results go down in C. Hit OK. Our A is 27.628. 27.628. Our slope is, I think, positive 0.052 times x. We're just filling in the A and the B in formula. Okay. I would also at this point grab the R, 0.874. We would call that relatively strong. So I'm expecting this to work as long as there's no big patterns here, okay? So 2, we're going to look at the graph. Does the graph itself appear linear? Well, chirps and temperature. Let's graph it. Go down here on the X, toss chirps. On the Y, temperature. Does that appear to have an overall linear trend? If you want to add the line to this, you can. Analyze regression A plus BX. Notice that is the formula we got. Okay, so let's go ahead and sketch this. One, 2, 3, 4. Let's see what that looks like. Oh, that one should have been a little further over. Okay, and 1, 2, 3, and up. and one above, like that. And then the line kind of went through these, try to make it fit how it overall looks, but that's a pretty good sketch. So we're sketching that line. It appears linear. Third, we look at the residual plot. How do I get that residual plot? It is under Analyze, Residual Plot, sketch it. Overall, no big pattern. I shouldn't see like, oh, well, this went up, down, up, down, up, down. Oh, the next one's going to go up and down. It's jumping around. So then you sketch it. 3. Oh, that point should have been over here. And down, up, down. And up, down. No pattern. This implies linearity. So what can we do? We can predict. Predict 3,000 chirp. 3,000 is our x. Take the equation, 27.628 plus 0.052 times 3,000. 27.628 plus 0.052 times 3,000. We are predicting 183.628. 8. Jeez. All right, so we're all ready to move on, right? I hope somebody's stopping me because there's something we talked about. We talked about extrapolation. Do we have anything close to 3,000 chirps in our table? That makes absolutely no sense, right? We have our lowest is 882 or 864, sorry. Our highest is 1200. We do not have 3,000 chirps. The other thing should have stopped you is this is temperature. We're talking about 183 degrees Fahrenheit. If that cricket's chirping, it's like a small scream of death, right? It's got like 3,000 chirps per minute. It's just screaming at you. It's dying from the heat. That's just sick, okay? This is not valid. Even though the linear pattern is valid, do not predict outside of this. This is not valid. How do I know? Even though the line is valid, this is extrapolation. And do not do extrapolation. Last but not least on this, here I've got the numbers. I'm going to go ahead and go a little faster on this one. We've checked the whole linearity, so I'm just going to go get the equation and use it to predict. There it was. Jeez. All right, so this was commuters and parking spots. So commuters and parking spots. I'll put PS. All right, so how do I get the least squared regression? Just go to calculations and choose linear regression. Oh my goodness, sometimes. All right, menu, stats, calculation, 4 for linear regression. Our x list was in A. Our y list was in B. And make sure the results are going in C. our equation, 89.4882. 89.4882 plus 0.409344. Okay, so is this a strong relationship? I'm going to stop for a second since we have it already and go down and go look at R. R is 0.901, so that's a good argument. .901, that would be good. If I wanted to look at the other two, and I'm not going to put them on this time, but I would graph, what was it, parking spots. So that was, I don't know, commuters. So commuters against parking spots. It appears linear. I can analyze. Notice residuals aren't lit. They don't get lit unless you add the line. Once I add the line, then I can do the residual plot. And both of those would support linearity, so we're going to go ahead and keep going on this, okay? We're going to use this to predict. What if this has 2,804 commuters? Can we predict how many parking spots we should have? Well, y hat is equal to 89.4882 plus 0.409334 times the x. 2,804 commuters. 89.4882 plus 0.409334. 0.409334 times how many commuters? About 2,804. So we are predicting 1,237.26. So since I need 0.26, we probably need 1,238 parking spots. This is valid, not extrapolation. We had numbers around 2,800, okay, and we had a good linear model. Before I go into the last thing, I want to make sure we understand one more thing here. I will be asking you to do things quickly. We expect, yeah, X was commuters. If there are 0 commuters, you would still need the y-intercept, A, 89.4 parking spots. Somewhat ridiculous in the situation. Keep in mind, right, you're going to have 0 commuters. Probably if nobody's coming, you're not going to need any parking spots. But remember, this is serious extrapolation of the situation. We didn't have anything close to 0 commuters. So this doesn't make sense. So you have to check for extrapolation. But there are times where the y-intercept does make sense. This one, it doesn't. Okay? But we also need to be able to predict the B is our slope. And the way we interpret this is we say, we expect y to change by whatever b is. Changing y will change x. As x changes by 1 and whatever unit it is. So in the context of this question, we would say we expect the y, which is the parking spots, to change to its positive, so we can say increase, by 0.409 x, which is the computers, changes by 1. So for every computer, we need 0.409 parking spots. That's what that slope is saying. That's what we would expect over time. For every 2 to 3 commuters, we'll need another parking spot. That's kind of what this says. Okay? So that's going to be something to use on the quiz. It's maybe a little more advanced, but that is something I want you to do. The only other thing that we have to interpret is r squared. R squared is known as the percentage of y, or the technical variation of y, if you want to be proper here. In the y, or in the line, LSRL. LSRL, jeez. LSRL explained by x. Well, how do I get here? Well, it gave it to us, but really it's just as easy as saying, well, if I know r is 0.901, what's 0.901 squared? That's r squared. 81% of the data is explained by x. I'm going to go back to the table. If I look at that, r squared, 81% of the data is explained by x. So, 81% of the variation in y can be explained by x. Okay. Last but not least, let's talk residuals. We'll just do a couple of these. Residuals, there's a formula for this. I just know it as actual minus predicted. Actual y value minus predicted y value. The actual y value will be something they give us. The predicted will be a y hat. Both of these will have the same x. So the same x, I'll look at the y. This will actually come from the table. So from the table, we'll get the actual y. The predicted, we will get by plugging in the x to get the predicted. A residual plot is where we plot all the x values against all of their residuals. We've already seen a couple of those, okay? But when I say what is the residual for a mother's height of 64 inches, this is using example 1, that is an x. What is the residual? Basically, how far off is our prediction for a mother's height of 64 inches? Let's go back to the table. So at 64 inches, the daughter's height is 65.3. That So at 64 inches, the daughter's height is 65.3. That is the actual y. That is the 65.3 is what I will use for the actual. Minus, how do I get the predicted? I plug the 64 into the least square regression for mother's height. So let's go back to the calculator real quick. Mother's height is way back here. Mother's height, here was our equation, 22.9534 plus 0.639, it's fine, times, what's the x? Well, We predicted at 64 inches. So 22.95 plus 0.639 times that 64. That's where we plugged it in. That gives me a predicted value of 63.849. So 65.3 minus 60 minus that answer, we have a residual of 1.45. What does that mean? Our point fell above the predicted line by 1.45. This is how you do it. It's the actual from the table minus the predicted by plugging it in. The good news is, if you are doing what I asked you to with these graphs, remember we graphed it, we did the residual. Do you remember that we just did 64? There's that point right there, right? The 65.3 was the actual y value. Look down here at the residual plot. I go over that point. What is the residual for that point? 1.44. Isn't that the residual we got? With some round off error. So if you use your calculator smart, it actually gives you the residuals. I guess use your calculator smartly. I can't speak smart. That'll be good. All right. Let's do one more. What is the residual for 900 chirps? I guess we could do the other two. The residual for 900 chirps would be the actual 900 chirps. So let's go to the actual table for chirps. Right there. 979.6. That's the actual y value. Minus predicted. Well, I get the predicted from the chirps. Y hat equals 27.628. Plus, how about 0.0523? Times, what's the predicted? That's our x, right? 900. So 27.628 plus 0.00. No, is it just 0.523? Times the 900. That gives me a y hat of 74.698. So what is 79.6 minus 74.698? Actual minus predicted, about 4.9. That would be the residual. That is how far off the actual is from the predicted. I can double check this. If you've done the graph at 900 chirps, where's 900 chirps? Right here. Go down here, 4.93. Some round off errors. So you might want to keep that in your calculator. Depending on your homework, they might want a little more exact. What is the residual for 1,350 commuters? Well, to do this, though, you would have had to graph the commuters, find the 1,250, or is it 1,350? Yes, 1,350. Find that down here. I need that point. Find that down here. That would have a residual of 34. Okay. That's a lot, but this shouldn't be a hard section, so kind of work through it. We have a couple more videos, and then we're pretty much done with the notes, so keep it up, guys.